Hello everyone, this is your tutor AB. Today we're going to be solving a problem from the IB May 2025 specimen paper. This is a paper 2 problem. Let's get started. From the look of this problem, it seems that it's relating to the Millikan's oil drop experiment. If you don't understand how this experiment works, I highly recommend you do find out on YouTube or some other way, because this is a very important physics concept and it has really revolutionized the study of physics. Okay, let's get started. The diagram shows two parallel conducting plates that are oppositely charged. Part A. Draw the electric field lines due to the charged plates. Okay. So how do we draw this? When you have two charged plates like this, the electric field lines always go from the positive to the negative end, right? So we can draw it like that. The arrow will go downwards and they'll be mostly equally spaced like so. But one more thing to note is that at the edges of this plate, the field lines will curve like so. They will curve. And you must make sure you curve them, because this is the nature of electric field lines between two charged plates. You'll have a curve and they'll be equally spaced in the middle. Okay. Part 2. The potential difference between the plates is 960 volts and the distance between them is 8 millimeters. Calculate the electric field strength E between the plates. Now in your data booklets, you have an equation E is equal to V over D, right? This is in your data booklets and we have all the necessary values to fill in this equation. We can say that E is equal to the potential difference 960 volts over the distance between them. That's what D represents, and D needs to be in meters. However, we are given it in millimeters, so the conversion between meters to millimeters is to the power of -3. So we can say 8 into 10 to the power of -3. Okay, and putting this in my calculator, what do I get? 960. You get 120,000 newtons per coulomb, or in scientific notation you can write it as 1.2 into 10 to the power of 1, 2, 3, 4, 5. 10 to the power of 5 Newton per coulomb. Okay. Second part, B. In an experiment, an oil drop is introduced into the space between the plates through a small hole in the upper plate. The oil drop moves through the air in a tube before falling between the plates. Explain why the oil drop becomes charged as it falls through the tube. Okay, so what we need to understand is while it's being dropped through the tube, it's going to collide with the walls of the tube. This collision creates friction, and friction will of course give this oil drop some charge. So we can say through friction caused by the oil drops, collisions with the walls of the tube. The walls of the tube. Because as you know, when you drop something, it's going to collide with the walls will create some friction, and this friction leads to a charge on the oil drop. Okay, that's this one marker done. Part C. The oil drop is observed to be stationary in the space between plates. Buoyancy is one of the forces acting on the drop. The density of oil is 730 times greater than that of air. Show that the buoyancy force is much smaller than the weight. Okay. So how could we show this? Well, to do such a problem, we need to create a ratio. What do I mean? We need to find out what is the buoyancy force by the weight. And this ratio, whether if it's greater than 1 or less than 1, will tell us the comparison of this numerator to the denominator. If this fraction is greater than 1 I know that buoyancy force is greater than weight, and if this fraction is less than 1, then I know that weight is greater than buoyancy force. In the case, I want to show the second case. Okay, so what are the things I need to do? What is the equation for buoyancy? First, let me write down some variables beforehand. The equation for buoyancy, Fb, is equal to rho, the density of air, by the volume of air displaced times gravity. Okay, and weight, as we know, is mass into gravity, and mass can be said as volume into density. So then we're left with volume of the air displaced times by the density of oil, and we know the density of oil is 730 times greater than that of air. So I can write rho O, the density of oil, is equal to 730 times rho A, can I not? So I'll substitute that here. So I'll say 730 times rho A times G. Okay, and these are my two expressions. Now if I divide them like so, I find that rho A cancel, the volume of air and the volume of air cancel, and gravity cancel. So I'm left with buoyancy over weight is equal to 1 over 730, which if I put in my calculator is equal to 1.4 into 10 to the power of, you can say 10 to the power of negative 3. Okay, and hence I can say that FB is much smaller than W. Okay, essentially all I did was find the expression for buoyancy and weight, and if this ratio of expression is greater than 1, I know that buoyancy is greater than weight. If it's less than 1, I know that weight is greater than buoyancy. In this case, since it's less than 1, I know that weight is greater than buoyancy, and hence I'm able to prove that buoyancy force is much smaller than weight. To recap, all I did was, for buoyancy, I know the formula is the density of air, the volume of air that is being displaced, times gravity. This is given in a data booklet. And the formula for weight is mass into gravity, where mass can be written as volume times density times gravity. This is the new expression for weight, and we know the density of oil is equal to 730 times the density of air, so that's what I substituted for density. And of course we have the volume of air that's being displaced, and so if I divide these two, FB by W, I can see that rho A cancel, G and G cancel, VA cancel, so I'm left with 1 over 730, and since this is smaller than 1, I know I'm able to prove this statement. Okay, draw the forces acting on the oil drop, ignoring the buoyancy force. Okay, so how do we do this? We know that the drop is stationary. Stationary means that the forces, the vertical forces on the oil drop, are equal to each other. They're equal and opposite. So what are the only forces on this oil drop ignoring the buoyancy force? So saying ignore. We know there is a weight, which is equal to mass into gravity, and we know of course there is a electric force, F is equal to EQ. These two are equal to each other, and because they're equal to each other, summation of vertical forces is 0, and so we know that this drop is in equilibrium. Okay, show that the electric charge in the drop is given by this statement right there, where rho A is the density of oil and V is the volume of the oil drop. As we know, this oil drop is stationary. Okay, and when it's stationary, we know that the summation of the vertical forces must be equal to 0. So using this diagram above, I know what are the two vertical forces that are acting on it. I know that first you have an electric force EQ, which is equal to my weight mg. Okay, and I know that m can also be written as the volume of the volume times the density of oil. This is how mass can also be written like. So instead of m, I can substitute this into this expression. EQ is equal to this right there. So let's put that in there. So I get V rho 0 G, and again I can rewrite this to say Q is equal to, let's write it in the proper form, rho Vg over E. And I have proven this expression right there. Okay, state the sign on the oil drop. I know that this oil drop is negative. Why is it negative? Let's take a look. We know that there's an electric force acting upwards on this oil drop. Okay, and this is a good diagram to show the oil drop. Suppose the oil drop is right there and there's an electric force upwards, right? There's an electric force upwards. What does this tell us? There's a positive side here and a negative side here. Because it's being attracted to the positive side, the positive charged plate, I know that this is a negative oil drop. Because if it were a positive oil drop, it would be going the opposite way. It would be going downwards towards the negative charged plate, right? So due to the direction of the attraction, direction of the force, I am able to conclude what is the sign of this oil drop. Okay. The electric field is turned off. The oil drop falls vertically, reaching a constant speed v. Outlined y for this drop, rho gv is equal to 6 pi eta rv, where eta is the viscosity of air and r is the radius of the oil drop. Okay, so this is what we need to understand. Going back to this previous diagram, the electric field is turned off. So now we no longer have this EQ. So for case 2, right, let's call this case 2, I have an oil drop, I have a weight, and I must have an opposing force, because what is terminal velocity? Terminal velocity, excuse me, terminal velocity refers to the state is when summation of vertical forces is equal to 0, and because I no longer have a electric force, there still must be some force to balance out this weight. And what is that weight? What is that force? That's going to be your drag force. So in case 2, now you have a drag force, and this drag force is 6 pi r eta v. This is given in your data booklet. This drag force will be equal to your mg, and when they are equal, the summation of your forces is going to be equal to 0, and then it will hit translational equilibrium. So terminal velocity, so I'll answer this question. So terminal velocity is when summation of forces in the y direction is equal to 0. So drag force is going to be equal to weight, and so we can say that 6 pi r eta v will be equal to your weight, which is equal to rho of oil g v, right? Because we know that mass is nothing but volume into the rho of oil. So that's basically how we can answer this question. There's no longer an electric force, so there still must be some force in place of this electric force to balance out the forces on this oil drop, because it reaches a terminal velocity. And so this extra force is going to be your viscous or drag force, and this drag force will equal to your weight, which is given by the statement. And so we are able to tell that this will reach the terminal velocity, and this statement is proven. Okay. Part 2. Show that the charge on the oil drop is about 4.8 into 10 to the power of negative 19 coulombs, and the following data is available. Now, using the concept that we got beforehand, we can solve this question. How do I do this? Well, I know that in this case, I need to find out what is the charge on the oil drop. Well, I can tell that the charge on this oil drop, QE, is going to be equal to the drag force, right? It's going to be equal to the drag force of this particular oil drop, which is going to be given by 6 pi eta RV. 6 pi eta RV. Now, I need to find out what's the charge. So simply, I can just divide Q is equal to 6 pi eta RV over E. And what does this give me? I get 6 times pi times eta is 1.6 into 10 to the power of negative 5 times, let me just move this to the side so it's a bit easier to work with. Sorry for that. Okay, let's just move this a bit like that. Eta is 1.6 times to the power of negative 5. Then we know that the radius is 1.36 micrometer. So 1.36 into 10 to the power of negative 6 times by finally velocity, which is given by 0.14 millimeter per second. So that I can write it as 0.14 into 10 to the power of negative 3, and this whole thing over the electric field which I calculated right at the beginning, which was equal to 1.2 to 10 to the power of negative 5. So putting this in my calculator, what do I get? Let's see. Make sure you put all the numbers correctly. Okay. Into. Also make sure you convert all the units to the right one that we need. In this case, we need to convert micrometer to meter and millimeter per second to meter per second. So all these conversion factors are given in your data booklet. So just be careful about that. Okay. So I get that Q is equal to 4.79 into 10 to the power of negative 19 coulombs. And of course, I can then say that this is roundabout equal to 4.8 into 10 to the power of negative 19 coulombs. Okay, that's your answer. That's this proven. Okay, now the last part. The oil drop splits into two parts of equal masses. Both are charged. Deduce the net charge on each part. The key finding of the Millikan's oil drop experiment, which this question is based off, is that the charge on the oil drop is always going to be a factor of the elementary charge. Elementary charge is E is equal to 1.6 into 10 to the power of negative 19. The charges are always quantized. So I can say the charges are quantized. Okay, and because the oil drop splits into two parts of equal mass, right, I know that this 4.8 into 10 to the power of negative 19 has to split into two charges, and because they have to be a factor of 1.6, I know that the charges will have to be 1e and 2e respectively. Okay, why? Because I know that 4.8 is equal to 1.6 times 3, and because they're equal to two parts, it needs to be in a 1:2 ratio, because both need to be a factor of 1.6, and so I can say that the charges will be 1e and 2e respectively. Thank you for watching. Please like and subscribe. If you have any questions, leave it down below and I'll answer it as soon as possible. Thank you for watching.